right, I had a few requests to go over some of the problems from the Week 6 AP Calc review, so I'm going to go over those. So this one says we need a graphing calculator, and it says grain is being added to a silo at time t equals 0. The silo is empty. The rate at which grain is being added is modeled by the differentiable function g of t, which is measured in cubic feet per minute for t between 0 and 8 minutes. Selected values of g of t are given in the table above. Using the data in the table, approximate g prime. Using correct units, interpret the meaning of g prime in the context of the problem. So g prime of 3. So we'll say g prime of 3 is approximately equal to, and we're just going to use the closest points to 3 to get an estimate. So we're going to use just our Algebra 1 definition of slope. And the closest points that we have to 3 are 1 and 5. So these are the 2 points we'll be using to approximate g prime of 3. So we're going to do 20.5 minus 15.1 over 5 minus 1. That should just go into your calculator and we'll get 1.35. Now we're asked to interpret this, so I'm just going to write out a quick sentence. At time t equals 3 minutes, the rate at which grain is being added to the silo is increasing since it's positive at a rate of 1.35 cubic feet per minute squared. All right, so that's part A. Move on to part B. Write an integral expression that represents the total amount of grain added to the silo from time t equals 0 to t equals 8, and then use a right Riemann sum with 4 subintervals indicated by the data in the table to approximate the integral. All right, so our integral then, I'll just say, see. So it's going to be integral 0 to 8 g of t dt would give us the total amount of grain added to the silo over those first 8 minutes. And so we're going to say that's approximately equal to, so if I want to use a right Riemann sum, what I always tell you guys to do is just kind of sketch out a rough scatter plot of what's going on. So I have g of t, and I have t, and my x values are 0, 1, 5, 6, and 8. So say 1, 5, 6, and 8. And then I don't really care what the y values are, just that there are y values, right? And so we're going to be using right Riemann sums. So on my first subinterval, I would want to use the right-hand side to get the height of that rectangle. On my second subinterval, use the right-hand side to get the height of that rectangle, and so on. So that's going to be g of 1, that's the height of my first rectangle, and I'm going to multiply that by the width of my first subinterval. Now these subintervals have unequal widths, so you're actually going to have to calculate it each time. So that first subinterval has a width of 1. So g of 1 times 1 plus g of 5 times the second subinterval would have a width of 4, right? So G of 5 times 4 plus G of 6 times that subinterval has a width of 1 plus G of 8, and that last rectangle has a width of 2. All right, and so then we'll just go reference our table to get those y values, but you're going to end up with G of 1 is 15.1 times 1 plus 20.5 times 4 plus G of 6 is 18.3 times 1 plus 22.7 times 2. Pop that in your calculator, and we're going to get about 160.8 for our final answer. All right, part C. The grain in the silo is spoiling at a rate modeled by W of t equals 32 root sine pi t over 74, where W of t is measured in cubic feet per minute for t between 0 and 8 minutes. Use the result from part B to approximate the amount of unspoiled grain in the silo at time t equals 8. All right, so first, we're going to use our answer from part B, which was 160.8. So that's our approximation for the total amount of grain. And then we're going to subtract off that the amount of grain that has spoiled over those 8 minutes, which we'll find from the integral from 0 to 8 of that function W of t dt. So this should be done in your calculator. All right, so the first thing I'm going to do, I put the function for W of t into y1 in my calculator. And then we're just going to go to quit to the main screen. We'll go math and scroll down to the integral option. And I want to go from 0 to 8. And we want to integrate whoops. I'm going to do alpha trace y1 dx. Okay, and then remember we wanted to do 160.8 minus that. And so that's approximately the amount of unspoiled grain. So 61. I'm going to say approximately equal to 61.749 cubic feet. All right, part D. Based on your model in part C, is the amount of unspoiled grain in the silo increasing or decreasing at time t equals 6? Show the work that leads to your answer. All right, so what we want to look at is our function is already a rate of change, right? Our original function g is the rate that grain enters the silo in cubic feet per minute. And W of t is also a rate, which is the rate at which grain spoils. So also in cubic feet per minute. So all we need to look at here is we want to look at G of 6 minus W of 6. And we want to see if that's positive, then the fresh grain entering the silo is entering faster than the grain is spoiling. and therefore the amount of unspoiled grain would be increasing. Versus if it's negative, the opposite would be true and it's decreasing. So we actually have g of 6, which is 18.3. W of 6, since we already have that function entered into our calculator in y1, I can just go alpha trace y1 of 6. Now you get about 16.063. So going back to our work here, I don't really even care what that value is. All I care to show is that that's greater than 0. Therefore, unspoiled grain is increasing at time t equals 6. All right, so we're going to move on to question 2. All right, question 2 is another calculator necessary problem. So this is going to be a physics one. A snail is traveling along a straight path. The snail's velocity can be modeled by v of t equals 1.4 log 1 plus t squared inches per minute for time between 0 and 15 minutes. Part A says find the acceleration of the snail at time t equals 5. So we want A of 5. Acceleration is the derivative of velocity. And since this is calculator necessary, we can totally just do this one in our calculator. I've gone ahead and put my velocity function into y1. So we're just going to quit to the main screen. We're going to go math, nderiv, whoops, so numerical derivative. I'm going to say d dx of y1. And I want that at x equals 5. So there we go. My velocity is 0.538. So 0.538, and then we need the units. Inches per minute squared. All right, what is the displacement of the snail over the time interval? 0 to 15 minutes. So for that one, displacement, we just want to integrate from 0 to 15 my velocity function, which once again can be done in the calculator. So I'm going to go back to math, and now we're going to use the fn int. I'm going to go from 0 to 15. All right, so 76.043 inches. And that just means the snail ended up 76.043 inches to the right of where it started at time 0. Now, it may have gone back and forth. That's not necessarily the total distance. It's the displacement. All right, at what time t equals, or at what time t between 0 and 15 is the snail's instantaneous velocity equal to its average velocity over the time interval? So first thing we want to do is find its average velocity, which is just going to be the velocity between the endpoints, right? So it's going to be v of 15 minus v of 0 over 15 minus 0. Once again, this is something we would want to do in our calculator. So my velocity function is in y1. So I'm just going to go Alright, so we'll do y1 of 15 minus y1 of 0 divided by 15. All right, so about 0.506. I'm going to say that's about 0.506 inches per minute. But the rest of this we can do in the calculator as well. So I want to store that in x. Great. And now I can go to y equals, and there's my velocity function. y2, I'll just place x. And I'm going to adjust my window. I only need to see between 0 and 15. And natural log gets big really, really slowly, so let's just go negative 1.5 to 5. Hopefully that'll be a decent window. Oh no. Invalid dimension probably means I have a stat plot turned on, which I do. Let me turn those off. Okay, now let's graph it. Okay, sorry about that. I just realized you can't use x as a constant in y equals, so I actually had to go in and type in y2 equals 0.5059. But here is the, we're looking for this point of intersection, right here. So I'm just going to use calc, intersect, first curve, enter, second curve, enter, guess. So for guess, you just want to move the cursor reasonably close to the point of intersection that you're looking for. Oh boy, this emulator is much slower than a regular calculator. All right, but that's what we're looking for. There we go. So x equals 0.6597, or 0.660, I guess, if we're rounding to 3 decimal places. So let's go back here. We'll say we set v of t equal to 0.506, which yielded t is approximately equal to, and I already forgot what the number was, 0.660. All right. So last part for this problem, an ant arrives at the snail's starting position at time t equals 12 minutes and follows the snail's path. During the interval 12 to 15 minutes, the ant travels in the same direction as the snail with a constant acceleration of 2 inches per minute. The ant catches up to the snail at time t equals 15 minutes. The ant's velocity at time t equals 12 is b inches per minute. Find the value of b. All right, so what we're given is the ant's constant acceleration is 2 inches per minute per minute. So the way we get from acceleration to velocity is take the antiderivative, right? So the antiderivative of acceleration will be velocity, but it'll be plus a constant because it's an indefinite integral. So I'm going to do the antiderivative of 2 dt is actually 2t plus some constant. So that is the velocity for my ant. Now, the antiderivative or the integral of velocity will give me displacement. So I can do that this way, right? I can go the integral from 12 to 15 of 2t plus c dt. This will give me the ant's displacement. But what we know is that the ant catches up to the snail at that point, right? At time 15. And we know the snail's displacement from part B is 76.043. So we know that this definite integral has to be equal to 76.043. And so now we're ready to evaluate, right? So the antiderivative of 2t is just going to be t squared plus ct, because c is a constant, and I want to evaluate that from 12 to 15. That's still going to be equal to 76.043. So plugging in 15 and then plugging in 12 and subtracting, we actually end up with 81 plus 3c, and that's going to be equal to 76.043. And now we just have an algebra problem, which is solving for c. So subtracting 81 and dividing by 3, we get c is approximately equal to negative 1.652. All right, now we're ready to fill in my velocity, right? So I can take that. Now I've solved for the c in my velocity function. So now I can say that the true velocity of the ant at any time t is 2t minus 1.652. And now the velocity of the ant at time 12, I could just plug in 12 for t and subtract. And we end up with about 22.348 inches per minute. Whew, that was a long one. All right, number 4. This one has some stuff that we didn't learn because it's from Unit 8. So Part B in particular, you don't need to do. Part A, you didn't even learn. I'm going to go over it just because it's not that bad. So they give us the function f, and they say R is the shaded region bounded by f in the horizontal line, y equals 3. Find the area of R. So anytime you're trying to find the area between two curves, all you have to do is integrate from their points of intersection. So I would go integral from -1 to 1, and you do top curve minus bottom curve. So in this case, I would do f of x minus 3 dx, and that's going to leave me with the area between the two curves. The other thing is, anytime you're trying to evaluate a definite integral, that should be done in your calculator for the exam. It'll just eliminate human error and save you time. So let's see, this one I would want to put my function f here in y1. So that's 6 over 1 plus and then I'll put 3 so we would want to go negative 1 to 1. Oh no. Of y1 minus y2 There we go, so about 3.425. So I'm going to have you skip part B, but part C is a really good one to do because it's a related rates problem, and I know that was a challenge. So it says, let h of x be the vertical distance between the point x, f of x, and the horizontal line y equals 3. Find the rate of change of h of x with respect to x at x equals 2. So vertical distance, all we need to do to find vertical distance between a curve and a line is subtract. So h of x for us is just f of x minus 3. So this is actually not too bad of a related rates problem. So h of x is f of x minus 3. So if I want to find the rate that h of x is changing at time x equals 2, all I have to do is go h prime of 2, which is just going to be f prime of 2 minus 3. Once again, we can do it in our very slow emulator of a calculator. So I'm going to do math. We're going to choose the differentiate option. We'll just go ddx. We're going to differentiate the same thing, which is y1 minus y2. y1 is our function. And then we're just going to tell it to find that derivative at x equals 2, and that's our answer. So negative 0.96. All right, and so all that means is that the vertical distance is decreasing at x equals 2, which hopefully makes sense, right? Because if we're at x equals 2, we're right here. And as you can see, as we move to the right of that, that vertical distance begins to decrease. All right, the last one I'm going to go over is question 5. right, so question 5 is a differential equation problem. So it says, during a chemical reaction, the function y equals f of t models the amount of substance present in grams at time t seconds. At the start of the reaction, there are 10 grams of the substance present. The function y equals f of t satisfies the following differential equation. And it says, use the tangent line to the graph at t equals 0 to approximate the amount of substance remaining at time t equals 2 seconds. So, first thing we need to do is write the equation of the tangent line. So I'll call that, I'm going to call that L of t. So to write the equation of a line, we need a point and a slope. They give us the point at t equals 0. There are 10 grams, so that's the point 0, 10. And then we can get the slope from our differential equation, which just tells us to plug in our y value and we will have the slope, right? So dy dt at t equals 10 is just going to be negative 0.02 times 10 squared, which is negative 2. So the equation of my line will just be negative 2t plus my y-intercept is 10. All right, so now I want to use that to estimate the approximate amount of substance remaining at time t equals 2. So all we'll do is L of 2, which would be negative 4 plus 10, which would be 6 grams. All right, there's part A. Part B, using the given differential equation, determine whether the graph of f could resemble the following graph and give a reason for your answer. And the answer is no. And the reason is this graph increases on part of its domain, but our differential equation tells us that it has a constant negative slope, right? And if the derivative is negative, the function has to be decreasing. All right. So C, find an expression for f of t by solving the differential equation with the initial condition. So we're just going to use a separation of variables here. So let's see, I'm going to divide over y, so I'll have 1 over y squared dy. We'll multiply over dt equals negative 0.02 dt. I'll just clean this up a little bit. I'll write that as y to the negative 2 dy equals negative 0.02 dt. And now we're ready to integrate. So on the left, we will add 1 to the exponent and divide by the new exponent. That gives me negative y to the negative 1 equals negative 0.02 t. Don't forget the constant. And now we're going to solve for our constant using the initial condition 0, 10. So negative 10 to the negative 1 equals negative 0.02 times 0 plus c. So basically c is negative 1/10. All right, so my function now becomes negative 1 over y equals negative 0.02 minus 1/10, negative 0.02 t. All right, and so just do some algebra to solve for y, so you can multiply y over, divide everything else to the other side, and you end up with y equals 1 over 0.02 t plus a tenth, which is 0.1. And this actually simplifies a little bit for, I mean, you could leave your answer that way, but if you want it to look nicer, that's actually 50 over t plus 5. All right, last part. So, determine whether the amount of substance is changing at an increasing or decreasing rate, and explain your answer. And so we want to find the second derivative. So we want we're going to take the derivative of the derivative, which is actually going to give us negative 0.04 y times y prime, or times dy dt. But we can just replace that dy dt with our original expression for dy dt, which was negative 0.02 y squared. And then multiplying that out, we get 0.008 y cubed. So that's our second derivative. And so I can say, since y is positive, our second derivative will also be positive. And we can say, therefore, the substance is increasing at an increasing rate. That's it. All right. Hope it helps.